Welcome to Theory of Computation, Pumping Lemma, Unit 2, Part 2. So I'm Dr. P.Ezhumalai, Professor and Head, CS Department, R.M.D.E.C College. Let us see the pumping lemma problems. Pumping lemma for regular languages. What is the pumping lemma? The pumping lemma is a property for all regular languages. How it is used? A technique that is used to show that a given language is not regular. To prove the given language is not regular, using for pumping lemma. The pumping lemma for regular languages. Let L be a regular language. L is be assuming that L is a regular language. Then there exists some constant n such that for every string W belongs to language. That is W modulus greater than or equal to n. There exists a way to break W into three parts. That is W equal X, Y, Z, such that Y is not to be empty. Modulus of xy less than or equal to n. For all I greater than or equal to 0, all strings of the form x, y power k, z belongs to L. If the condition of those three conditions satisfied, that language is called as a regular language. If it is not satisfied above three conditions, that language is not regular. Let us see example. Let assume that L is a regular. It should not have a DFA. Let n be a number of states in DFA. Any string W belongs to language statement, that is modulus of W greater than or equal to n. N is a number of states. We should have the form W equal to A1, A2 up to dot AM. So where M greater than or equal to n. So M is the number of strings in the word. That should be number of n is the number of states where M should be greater than or equal to n. Let the states traversed after reading the first input of n symbol to be P0, P1, dot up to extension of Pn, where there are n plus 1 P states while there are only n PDA states. So at least one state has to be repeated. That is Pi equal to Pj, where 0 less than or equal to I less than or equal to j less than or equal to n by PSP. Let us see that example. We should have able to break W into three substrings. That is called X, Y, Z as follows. Let X equal to A1, A2, dot AI. Y equal to AI plus 1, AI plus 2, dot AJ. Z equal to J plus 1, J plus 2, dot AM. Let see that three states. P0, Pi, Pm. P0 is the starting state. Pi equal to Pj is the middle state. Any string is repeated, that is called as a Y. So input P0 to Pji equal to X. Input Pi equal to Pm equal to Z. So the X, Y equal to repeated for Pi equal to Pj self loop. Let us see that Y is the path between them Pi plus 1. Similarly, Z is a path between the Pj to Pm. And now consider the another string Wk equal to X, Y power k, Z, where k greater than or equal to 0. Now let us, Y will be repeated number of times. Let us see that in case k equal to 0, the input will be DFA will reach the accepting state PFA. If k greater than or equal to 0, so DFA will loop for Y equal to k, finally reach the accepting state PM for Z. So in either case, W suffix k belongs to language. So this language is called regular language. If this proves that part 3 of the lemma. Now, so see that diagram. Part 1, since I less than j, so y not equal to empty. Then part 2, by PHP, the repetition of the states has to be occur within the first n symbols in W, where modulus of xy less than or equal to n. To prove that some languages not to be regular, let us see that not regular languages. Thank you for playing a person 2. Rule 1, we claim that language not to be regular. Rule 2, the adversary who claims the language is regular. So we show that adversary statement will lead to contradiction that implies pumping lemma cannot hold for the language. We will win that. This is one example for pumping lemma regular language. How to use the pumping lemma, the steps. So L is not regular. Next, adversary claims that L is a regular language and gives values of n that is not this pumping lemma language constant. Now, using n is number of states. Choose a string W belongs to language. The statement modulus of W greater than or equal to n. Using W as a template, construct other words WK of the form X, Y power K, Z and show that at least one such WK belongs to L. So if it belongs to L means that language is not regular. Using the pumping lemma, what do we do? So adverse case claims L is regular, proven N. So using N is number of states, we construct our template string W. Demonstrate the adversary either through pumping lemma up or down on W. That string W not belongs to L such that the language is not regular. Example for pumping lemma W, where W is a binary string which is equal to zeros and ones. Let us see that L is not regular. Prove. By contradiction, L will be irregular. Let us the program pumping lemma language constant should be exist where N there is a pumping lemma constant where see that consider the input 0 power n 1 power n our choice. So any number of zeros, any number of ones. In the pumping lemma, we should be able to break W into X, Y, Z such that Y should not be empty. XY modulus less than or equal to n. For all I, for all k greater than equal to 0, the string X, Y power K, Z is also in n. This is the pumping lemma concept. So, because the modulus of XY less than or equal to n, and XY should contain at least one input, zeros. Okay, therefore, X can contain at least n minus 1 zeros. Also, all the n ones must be inside Z. So by 3, any string of the form X, Y power K, Z belongs to the language for all I greater than equal to 0. In case K equals 0, X, Z at most n minus 1 zeros, but also n 1 state. So similarly, so the string is not belongs to the is in the form last accepting state. So the given language is probably not our assumption is a contradiction. So this language is not regular. Thank you.